Hello and welcome to another tutorial. In this tutorial, I'm going to discuss in more details how to implement particle swarm optimization in Java. To recap, we discussed the main algorithm for updating the position and velocity of each particle as they go through the random walk, and to also get to the optimal position in terms of minimizing or maximizing a given fitness function. We said that we have this term C2R2, the best guess position for the particle I, and the current position of particle I. Okay, and this was based on this was mimicking the swarms like behavior. Okay, and these are the range of values that we typically choose. W is 0.5 or anything between 0.5 0.9, and this W actually determines whether this inertia weight W determines whether we want to get to a local minima or maxima or a global minima or maxima. So you can read the literature to understand how changing this parameter leads the particles to a local or global extrema. All right, and we said that R1 and R2 are the random parameters that generate the random walk behavior. All right, now in terms of the algorithm, I took this pseudocode from Wikipedia, which is basically exactly what I'm going to implement is Java. So it says that create S particles. So we have S particles, so the dimensionality of the search space is S. We have S particles. For each particle I equals 1 to S, do this algorithm. Initialize the particle's position with a uniformly distributed random vector. So this interval is basically the interval for each variable of the function. If you recall, we said that the dimensionality of a particle is equal to the dimensionality of the function, the fitness function, the function that we want to optimize. So we pick a randomly, basically a uniformly random choice for the values of each variable in the given interval, in the search interval, and then initialize the particle's best known position to its initial position. So at the beginning, right when we create the particle, we set the particle's best position to the current position. All right, and this to recall, this best position basically keeps track of how the movement of the particle affects the values of the function that we want to optimize. All right, so we only optimize in each step, we update the position, but in order to update the best position, we compare the value of the function at the current position with the value of the function at the best position. And that's where the objective of the optimization or the objective of the swarm actually comes into play. So we only update the best position if it helps to get a better value for the function towards the general optimization goal. Now to recap, F is the fitness function, the function that we want to optimize, and it says that if F of the best current position is less than F of G, then update the swarm's best known position. So G is basically the swarm's best known position, which go through all the particles and see which best position of which particle gives you the best value for the function. If you want to minimize it, which G is basically the position of one of the particles that give you the minimum value for the function. Okay, and then it says that initialize the particle's velocity to some uniform distribution between minus to plus of the interval. Now I'm not going to do this, I'm just going to initialize it to 0. It doesn't really matter that much, so it doesn't really matter. So I'm going to initialize it to 0 here. And then while a termination criterion is not met, so what is the termination criterion? It could be that I don't know, a threshold for the value of the function, and then or it could just simply be the number of iterations. So I'm going to choose the number of iterations as the as the termination. So I'm gonna tell it, okay, just iterate for 100 steps 100 times and then stop, right? So termination criteria could be based on the fitness function or could just simply be the number of iterations. Now obviously you have to look at the kind of visually have a visualization or have a plot of how the value of the function is changing over each iteration and whether or not it actually converges to a minimum or maximum. That's very important. So while we're not met with the termination condition for each particle and for each dimension or each variable, we're going to pick our random numbers R1 and R2 or R particle and R group. So if you recall in the previous slide, I called them R1 and R2, and I mentioned that this first term is the particle behavior, the second term is the group behavior or the swarms behavior. Okay, so in this algorithm it's calling them RP, R particle, and R group, and these are random numbers between 0 and 1, a uniformly chosen random number. And update the particle's velocity. So we're going to update the velocity first with W times the current velocity. Phi particle is basically the C1, the social coefficient, social interaction coefficient. C1 or phi p R particle, best position of the particle minus the current position. That's exactly what we had here. Best position minus the current position. Plus phi group, which is C2, R group, which is R2, group best position minus the particle current position. So group best position at this iteration step minus the particle best position. So this is our movement equation, and then we're going to update the position based on the current position plus the velocity that we just updated. Okay, and then we check for the swarm's objective, and then this is something important. So we update and check whether or not for each particle, remember this if statement is iterating over the particles. So for each particle we check its best position and the updated position and see whether or not we have to update the best position. Okay, and then similarly the same thing for the group best position. We check it with the best position of each particle and we see whether or not we want to optimize it. As what you can see is that this algorithm, because we're checking with the less than sign, it means that we're trying to minimize the function. So if you just exactly implement this algorithm, this pseudocode, you have an algorithm, a PSO algorithm that is always minimizing the function. It doesn't maximize, because once the best position of the particle is it gives you a value for the function which is less than what we have so far, we update the position, the group best position. Okay, so what if we want to maximize? We just return the sign here. Instead of less than, we have greater than. All right, that's one way. Or in order not to change the algorithm, what I typically do is I multiply the fitness function by a negative sign. So instead of f, if I have negative f here, negative f of xi is less than negative f of pi, then if you multiply by f, the less than becomes greater than, f of xi greater than f of pi. Alright, so if the user chooses to maximize the function, the way I implement this algorithm is that I keep it as is, but then right at the beginning I multiply the fitness function by negative 1. It just changes its sign and this algorithm remains intact. Okay, so as you can see, this is very simple. Create the particles, initialize them to some random positions, and then initialize the velocity to whatever you want. I'm going to initialize it to 0, and then for each particle and for each dimension in each variable, update it. And so what I'm going to do, instead of having this for loop, I'm going to create a n-dimensional vector and then overload the operators plus, minus, and multiply them by a simple number for these vectors. so that I don't have this for loop anyways again. So I just create vectors and write this down using the operator overloading. All right, and let's head to Eclipse and try to implement this. So I have already created a PSO project, demo PSO, and I have already implemented the classes and the objects that we need. Well, here I'm just going to go through them and walk you through the code so that we save some time. Now the first thing we need is a fitness function, and as you probably are familiar with the routine so far if you've watched my previous videos, we use an interface. It's always the best thing to do. If we have a function, we just define it as an interface, and this function returns has a double method. Remember, this interface, so this is a public interface, so this method signature implicitly has the public modifier plus abstract modifier. Remember, interfaces could only have two access modifiers, public or default, which means package level access. Obviously, I want this to be public so that other codes outside the package can access this. And then this method is in a public interface, so it should imply public method plus abstract. All these methods and abstract. And to refresh your memory, an interface from JDK 8, Java 8 can also have default methods in case in the future you want to evolve the interface without breaking the codes of the current implementations or without causing any compatibility issues. In the future, you just can use a default method, all right? But again, our intention here to have a functional interface, so I'm going to annotate it. It's not necessary, but it's good to reinforce this fact. All right, so this is our interface, and this function has a undetermined number of variables, which I call them args, and this is a vararg implementation, variable argument, vararg implementation, which is a very handy thing to do. All right, and the alternative, if you recall, is have something like value an array of doubles of args. But I'm going to, and as I mentioned, at the compile time, the compiler actually replaces this double dot 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 with an array of doubles. All right, so these two are exactly equivalent, but this has more flexibility. In case that you don't actually need to define an array and pass it, you can just use value x1, x2, etc. Right? And again, compiler changes this into an array and then passes it to the method, which is very useful. So vararg is always preferred over just having an array of doubles. All right. Now the next thing I'm going to implement is an object called interval. This is just simply to mimic the behavior on interval and also get the random number that we want from it. All right. And so in the interval we have a start end, and the interval constructor is takes an double as the start and double as end and initializes these two variables, and these actually could be private variables. We don't really care that much. Let's make them private. And the class itself is default level access. Default has default access modifier, which means it only visible in the package. It's not visible outside the package, and that's what we want. And I'll show you why I'm defining this as this class as a package level access. I don't want anyone outside the package to be able to access it, but then later on I define an static method to be able to get access to this interval, which is more convenient than using the new keyword and each time just creating an object of interval. All right. Obviously we have these getters. I don't want to have a setter. Doesn't really make any sense to have that. And then to a string method, I have already overridden it, just have it there. And then this method is what we want. So this is the useful method. for uniform random choice, all right, in the interval. So I call it public double get random. And again, these methods don't need to be public because the class only has default level access, so they could just be a package level access. Okay, all right, now because okay, so these two string methods should be public because in the object it's public. So if we go back here, it's public in the object method, object class, so we should keep it public. We cannot reduce the visibility, but the other methods are just default level or package level access because the class itself is package level access. So here I create R, which is a random number, and if you just call the random method, it returns a double value with a positive sign greater than or equal to 0 and less than to 1. All right, pseudo randomly values approximately uniform distribution from that range. So this returns 0 and 1. So R in 0 and 1. 0 is inclusive, 1 is exclusive. And then what I want to change this random number from 0 to 1 and map it to the start to end interval. So we want to map this to interval start and end. All right, and the way I'm going to do it, you just use this start plus end minus start times R, because R is between 0 and 1. So if R is 0, we get start. If R is 1, we get end. So we basically map it to the start and end. All right, so this is the interval. And then the next thing I'm going to create is a ND vector. I call it vector ND. And the reason I'm doing this, I want to overload the operators for addition, subtraction, and multiplication, which makes the life easier when we implement the movement of the particle. So this class also has a package level or default level access, so not visible to outside the package, which is fine. We don't want the user to basically get access to this. This is an intermediate class that we're going to use to implement the actual algorithm. So this vector has a dimension, integer, and an array of double values. And it has a constructor. It's a var constructor. So let's write it. Var constructor takes the variable argument length x and then assign it to the array here, and then also updates the dimension based on the length. All right, and then it doesn't have any setters. We don't want to mutate it, so it's immutable in terms that we don't have any setters. And then we define this method at some integer index, and it just returns the value of the array at that particular index. All right, and then we override the two string methods, something like this: a string builder, start with the open parentheses, append x comma, or we could just simply use the return arrays dot to a string, a double value of x. We could just simply use this, but I'm not going to use it. It's definitely useful for you to know the utility classes in the JDK and try to use them wherever possible. It just makes life easier. So operator overloading, addition. If we add a vector by a double number, we're just going to add that double number to all the elements and return a new vector ND. If we add it to a vector, or basically if we add it to the array of vectors, we're going to add each element of this array to its corresponding element in the X, and then return. Obviously what you need to care about that x dot length be equal to v dot length. I didn't implement it, but the reason I'm not implementing it is because the user is not going to access this class anyways because it's a package level access, and for what I'm going to do with this in the general algorithm of PSO, this condition is always true. There is no point during the algorithm that this condition is not satisfied. That's why I didn't actually put a check statement or an if statement here. But if you want to make this class public, instead of having a default class, you have a public class and open it to the user, then you have to take care of all these subtle things when you're writing the code. Make sure it doesn't break. The reverse addition, and then what is important for us are these two. Adding a vector nd to another vector nd. So this dot x at index I plus v dot x at index I, and the reverse addition. All right, these two are important in terms of addition. Same thing about subtraction. These two, subtracting a vector from a vector, and then reverse subtraction, v dot x minus this dot x at index I. And the other thing that is important for us is multiplying by a double value. Remember, multiplying a vector by a vector doesn't make any sense, but multiplying a vector by a real number makes sense. So multiply, you just multiply each value with the number, and reverse multiplication, and similarly division. And the only division that makes sense is to have the vector, which is this, divided by v, and then negation is minus this. All right, the reverse of the division, v divided by this, doesn't make any sense. You cannot divide a number by a vector. And then the negation. All right, so this is how the vector nd works. So let's close this. We have the interval and then the function. Now we go to particle. So this particle is also a package level access. So again, I don't want the user to directly interact with the particle. But I'm going to use this in the actual PSO. So this is again an intermediate class that I'm going to use. Package level access, no, not open or not accessible to the user outside of the package. All right, I don't want this to be part of the public API, but internally I'm going to use this. So internally PSO uses this particle class. Just have this in mind. All right, so what do we have? So n-dimensional particles, if you recall, the first thing is to define, again, these don't need to be public because we're not going to use this outside the package. So this could just be a default level access instead of public access. Doesn't really matter that much. So I'm going to make these all default level access. And in Eclipse, the default access are all these triangles. All right, if I make them public, maybe this is just a side note, they become circles. Green circle means public. A green circle with a dot is a field or a variable. A field green circle means a method, right? Triangle means default level or package level access. So we have this, so the dimension of the particle, which is equal to the number of variables that our function has, and then we have a vector nd for the position of the particle, vector nd for the velocity of the particle, a vector nd for the best position of the particle, and then a double value for the best value for the fitness function. Which basically this is tracking the particle motion in accordance to the swarm's objective. Okay, so each particle has a best position and best value, and also has a position and velocity. So we initialize the particle based on an array of intervals. Each interval corresponds to one of the variables. Obviously, this means that the length of this array of intervals should be equal to the dimension of the particle. All right, so we set the dimensionality based on the length, but then we have to make sure at some point that this dimensionality of the particle is equal to the dimensionality of the fitness function. For now, I'm just going to assume that it is the case. All right, so the dimension is equal to the length of this interval array, and then we create an array of double values for initial position, new double, and then for each index in this array we get its corresponding interval in this array. And if you recall, we had this get random method, which just makes simply creates a random number and then returns it. So we're initializing the position. The initial position of the particle is basically random numbers in the given intervals, and then the position becomes a vector nd of the initial position. The velocity is initialized to 0, so velocity is 0 vector, 0 0 0 etc., n dimensional. Best position is basically initialized to the position. If you recall that initialize the particle's best known position to its initial position, so we're doing that. And then the best value, we initialize it to a max, because right now I'm assuming that the objective is minimizing the particle. Doesn't really matter, but we can just initialize it to some number. And the reason that I'm doing this, because the particle the particle and the fitness function are completely separated, so that's the way I'm implementing it. If you recall, if you see here, it says that update later on update the swarm's best position based on the fitness function. So when we are creating the particles, we don't really care that much about the fitness function at the moment, so it's a separate entity, right? So I just initialize the best value based on some random number. Here I'm just setting it to the max value. All right. Now obviously I can have another constructor to get a list of intervals instead of an array of intervals, and the code is pretty much the same. The only thing that changes here is that from the list we get index I and then get random. Now you might be surprised that even this notation works here. Even though this intervals here is a list, and the reason that it works is because when we install the operator overloading plugin for Eclipse, it actually also has some extra things to enable this kind of access behavior. So whenever the compiler sees this, it replaces it with this method, get method. All right. But in order to be more clear about what we're doing, we can just use the get method. So the access to the elements of a list is also overloaded with the notation of the arrays. That sometimes makes life simpler in terms of we don't really need to change anything in this code. We just change the argument to a list. All right, so as we said, the particle only has one useful method, which is the move method, and for that we take the current position, the velocity, and then basically update the position. All right, updating the velocity is outside the particle. We just implement it in the PSO, and we also override the to a string method, and it just returns the position. All right. And if you recall, position is a vector nd, and we have already overridden the toString method for vector nd. So this should work. All right. And we can quickly check. Let's create a main method here, and particle p1 new particle interval. So I'm going to create a new interval, for example 2 and 4. Okay, maybe another one, new interval -2 and 2. As you can see, just writing all these news in the constructor is not convenient. That's why I have plans to do something else with this. But here I'm just going to quickly show you that how the toString method works. Actually, we don't need to call the toString method. The compiler does it for us. So we have a particle at these coordinates, right? So we can also have reduce the number of digits or decimal places that are being shown here, and we can use it. We can use the string.format method to do that. Alright, so this is the particle. It can move. Each particle can move. Now let's go to the actual PSO. Alright, so the very first thing that we need in the PSO is the parameters W, C1, C2. These are the fixed parameters, inertia, weight, and the social coefficients. And then we have the dimensionality of the search space, which is the number of particles. And then we have a flag for optimization goal. So this is swarms optimization or objective optimization goal, optimization goal. And then we have our fitness function that we set, and then a list of particles. All right, and then outside each particle for the swarm we also have swarms parameters. Basically swarms best position and value. And again, I'm going to assume that by default I'm minimizing, so I set the best value to max. Okay, and so in the constructor of PSO, what I'm going to do, I'm going to have a parameter for the number of particles, so the user should set how many particles it needs, and then the fitness function, and then an array of intervals. And again, the number of particles is what the user sets, the fitness function is what the user sets, and again this is an interface, so you can simply use a lambda expression. And then the particles, we initialize this array with empty or null values, and then add create new particles based on the intervals, an array of intervals. All right, so we create new and remember, each time we create a new particle, the position of the particle is completely random, because we're calling the random method from each interval, the get random method. So this ensures that the position of the particles each time we create a particle is completely random. And then we need to also set the guess best position, which again is completely random. Here we're setting this as a completely random value for the best position of the swarm. Now if we go to the algorithm, G is the best position of the swarm, and it says that check for this if statement for each particle, but I'm not going to do it. Doesn't really matter that much, because eventually we're going to do it here too, so we don't need to worry about that in the beginning. Okay, so we create the particles with random positions. Their velocity is automatically set to 0, and then it's being updated at each iteration step. The best position is also randomly chosen in the intervals. All right, okay. So this is the thing that I like to do here, is that so the interval class was basically package level access, and the reason is that I don't want the user to use the interval class to create intervals, because then each time the user has to use new keyword, and that's a little bit tedious if you have like 10-20 intervals. Instead, I create a static method and make it public. Now the PSO should be public because this is what the user actually interacts with. These variables could be public because the user can change them, but for now I'm going to make them package level access, so I don't want the user actually change them. We can have setters for the user, but for now these numbers are typically work in almost all cases, so the user doesn't really need to change these numbers. So this static interval method is very useful because the user can just directly call it without using the new keyword and just pass the star and end, and this just returns a new interval object, so it makes it easier, especially if the user imports this as a static method from the PSO. And then we have this flag for optimization objective, maximize or minimize. Set minimize could be true or false. If it's false, it means the objective is to maximize. Then we set the fitness function. We said the fitness method basically gets the value of the fitness function for this particle, so returns the value of the fitness function at the particle's position. And again, this is to make it more convenient to deal with particles and the function, because if we don't do that each time, we have to, from the particle, get its position and then get the x, which is the array that holds the values of the position, because position is a vector nd and the values are stored in x. And then from the fitness, we have to call the value. All right, so instead of doing this each time we want to evaluate the fitness function, we just write this function fitness. All right, but then the other trick here is this negative sign. So what I'm going to do, I'm going to implement exactly this algorithm, always this algorithm, which we know that it minimizes the function, and then I'm going to artificially reverse the sign. So reverse the sign of the fitness function to maximize it. So basically, if minimizing minus f is equivalent to maximizing f. All right, this is my point. So this fitness doesn't actually return the so maybe we should make it private because we don't want the user to actually work with this fitness method. And then we just define this to get the value of the fitness function at the particle's position, and also based on the minimize flag we artificially change its sign to maximize it. All right, and then we print particles, which is just a toString method, no problem. And then we're going to move the particles. So this, again, this is private because we don't want the user to use this. This is an internal method. So this is where the algorithm is actually happening. What we're going to do in the move particles method, we write a for loop, and in this for loop we update the velocity. Again, r1 and r2 are random numbers between 0 and 1. Okay, and then the new velocity is w times particle dot velocity plus c1 times r1 times particle base position minus particle dot position plus c2 times r2 times guess base position, which is from the swarm's position, minus particle base position. This is exactly the equation that we had. And then we say that assign the new velocity to the velocity of the particle and then move it. And if you recall, the move just changes the position, right? Velocity, add to the current position and update the position. All right, and then after moving the particle, what we're going to do, we're going to basically update particle position we did, and now these two checks for the particle's best position and the swarm's best position. All right, based on the objective. So I implemented them into these two separate methods. So one is update particle best position or particle best parameters, because it's the position and the value. And then we write a for loop for all the particles. We get the fitness value. And again, remember, the default is minimizing. That's why we reverse the sign of the fitness function. All right. And then we don't need to reverse this greater than to less than or whatever. If particle best value is greater than fitness value, which means we have to update. So best value is the fitness value, best position is the particle dot position. All right. So the particle is moving towards a better objective, towards the minimizing the function. Best value, the value of the fitness function at this position. And again, if you go back to the pseudocode, f of x is basically the current position, and then pi is the best position. All right. F of pi is the best particle's best value. That's how we defined it. Best value for a particle is the value of the fitness function at the best position of the particle, which comes from the previous steps, previous positions. If it's greater than the fitness value or the value of the function at the current position after updating it, we're going to update the best position and the best value. All right. So basically, this is just the history of the particle. History, keeping track of history of particle based on swarm's objective. So this is for particles, and obviously we have to have one for the swarm, right? Update guess best parameters. Guess is basically, when we say guess here, it means the swarm's behavior, swarm's parameters. So again, for each particle, we're going to get the fitness value, which is calculating the fitness function at the particle. And remember, this fitness function has been tricked a little bit with that artificial reverse sign for minimizing or maximizing. If guess best value is greater than the current value, fitness value, we update. All right. And again, the guess best value is, if you go back, is the value of the fitness function and the group's best position or the swarm's best position, this G, right? If this is greater than the fitness function for the particle, we update G with the current position, right? And we iterate through all the particles. So finally, what we're going to do, we're going to have a, and again, these two should be private. The user doesn't need to access these. Update method, but then we have a public method called solve, and the stop criteria is the number of iterations. So we write a while loop, and as long as the iteration step is less than the number of iterations, we update the particle's best parameters, best position and value, update the swarms. So the first one is particle properties, and then the swarm, update guess best params, which is related to the swarm's behavior. Let's write it, behavior, swarm's behavior. And after that, we're going to move particles, and then increase the iterations. That's it. That's all that there is here. I guess I'm doing the updates first and then updating the position. Doesn't really matter that much. So you can update the particles first, move the particles, update them, and then update the swarm. Alright, so I'm moving the particles after updating the information. You can move the particles first and then update the information. Doesn't really make that much difference. And then we have two methods for getting the best value, which returns the maximum or minimum that we're looking for the fitness function. And again, be careful here because we change the behavior of the fitness function with the reverse sign. So if the minimize flag is set, guess best value is the exact value of the fitness function. Otherwise, guess best value or the swarm's best value is the reverse or negative of the function. So we have to do this. Best position is just the swarm's best position or guess best position. All right. And finally, we have this test. So I will have one more video to look more into the testing the PSO, but here is just a quick test. I have a main method. I create a fitness function using a lambda expression, and remember this parameter here is an array, so we have to call its 0th element for a 1D function, which is a sine of x. All right, so make sure you understand this t is an array. And then we create a PSO with 10 particles with our fitness function, and we want to search for do the optimization in the 0 and pi interval. And again, this interval is the method that returns an interval class object, so we don't need to write the new keyword each time. Okay, I want to maximize this, and I already know that this function has a maximum point at, so max, we already know the answer, right? X equals pi over 2. And we want to solve for, let's say, 10 iterations, and I'm going to print the best value and best position. Let's see. So the best value of the function is 0.99999, almost 1, which is we expected. Sine at pi over 2 is 1. And the best position is 1.570806. This is very close to pi over 2. Let's print pi over 2. One point 57079, 1.5698. So very close to 1.570. All right. So as you can see, with just only 10 iterations, we got very close to the optimal value, and the optimal value for the function and also the variable, right? And all this iteration doesn't do anything. It's just a couple of multiplications and summations and a few ifs. So there is no like expensive operations such as finding the gradient or whatever, right? So this is a very simple and quite fast method. Now if I increase the number of iterations, obviously this result should get more and more accurate. 1.57077963. So we pretty much have like 6-7 decimals of accuracy here, and again it was pretty fast. And hopefully you understand all the details of the PSO. We will look into more examples and more tests for the PSO in the next lecture. Thank you for watching, and I'll see you in the next video.